Okay, so we're still talking about enzymes. We're talking, or leading up to the transition state theory, but we have to back up a little bit and talk about chemical equations and just do some basic stuff from GChem. So if we're looking at the equation, S goes to P, right? So a simple substrate goes to product. We know that there's a forward and reverse reaction here. And we know that this will proceed at a rate K1 in the forward direction and K minus 1 in the reverse direction. We also know from our thermodynamics that we can define a KEQ that is simply equal to the concentration of product, so the concentration of the substrate. And we know that delta G is equal to negative RT natural log of the KQ. So from that we can tell quite a bit about the chemical equilibrium. So we know that KQ says that at equilibrium, or when the delta G is 0, what is the concentration of products and substrates? If the KQ is greater than 1, there are more products than substrates, and the forward reaction is favored. If it's less than 1, there's more substrate than product, and the reverse reaction is favored. And if they're equivalent to each other, then the delta G is equal to 0. So this tells you about the energy in a chemical reaction, but it doesn't say anything about the rate of the reaction or how fast that reaction will occur. And if we go to our good old reaction coordinate plot here, then we can look at something like this. So oops, this is the S, this is the P. And so we can say that there's a delta G that's at one level here, at this level here. We know that because the products are at lower energy than the substrate, and this is an exergonic reaction, and there's a release of energy. The delta G in this case is going to be the difference between the delta G of the substrates versus delta G of the products. So this tells you whether equations are exergonic or endergonic, but it can't tell you how fast something will go. And I like the example of a match, right? So this is a matchbook from one of the best steak places in Atlanta, the Iberian Pig. And here, these matches are made of wood, right? And this wood is potential energy that can be used to make a fire. Now, we can leave that match on this table, and I would bet that for the duration of this talk, we will not see it spontaneously light. It wants to, right? Because the delta G is exothermic, it will release the energy. The energy is embedded in this match as potential energy. So it wants to spontaneously break down into carbon dioxide and water in the presence of oxygen, but it doesn't. And so the question is, what keeps it as a match and not lit? And that is the activation energy. And so the activation energy is just this. It's a little more energy, a bump on top of this reaction. Now note, the substrate and the product are unchanged, and the delta G of the reaction is unchanged. But you have to surmount this activation energy for this chemical reaction to go forward. And so for something like a match, the way you do that is simply by, of course, lighting it, right? And so now we have provided the activation energy for this reaction, and the substrate, in this case the wood, is being broken down to product, in this case carbon dioxide and water, and releasing energy in the process. So one way to get over this activation energy, many ways to get over it, is to provide the energy via some exogenous source. We can't do that in biological systems because we are isothermic. So we can't simply provide the energy to surmount the activation energy. And so what enzymes do and what all catalysts do are to shrink the activation energy. And so here's where we get into some good old chemistry. We know that the velocity of a reaction, and this is moles per second, is a function of the substrate concentration. And so if you remember from general chemistry, this is a first order reaction, and so the velocity, this is at V0 here, is equal to, is a function of the substrate concentration. It's a linear function of the substrate concentration and whatever this K1 is. And here, if velocity is in moles, molar per second, this is in moles, so then this one, or molar, so this has to be a units of per second, right? So the question is, what is that K? And that K1 here is equal to a long expression that I'm not going to make you know, but basically it's KB T H E times the delta G activation energy over RT, right? So here, this is a constant, this is a constant, this is temperature in Kelvin, this is the natural log function, E, and then here is the activation energy, right? And so what does this say? The rate of the reaction, the velocity of the reaction, is an inverse exponential function of the activation energy, right? And so a small decrease in the activation energy can lead to a large increase in the velocity or the rate of a reaction. And so this is the trick that the cells exploit. They use enzymes to shrink the activation energy and therefore dramatically increase the rate of a reaction. So just to look, and then this is the basic step, and we'll see this over and over again. If you look at the same reaction coordinate plot, here you have S, you have P, this is the delta G, which tells you how much energy is released in that reaction. Right. This is the activation energy, the difference between S and this peak, and that will give you information on the rate of the reaction. And so what an enzyme does is simply use that same reaction, somehow lower the activation energy, but not change the nature of the reaction. S is still S, P is still P. The enzyme's unchanged in that reaction. Just so this will be S plus enzyme is equal to ES, goes to ES, which then goes to E plus P. And so in this case, the enzyme leaves this reaction unchanged. The chemical reaction is the same one that we saw up here. This is the same reaction of S goes to P. It's simply that the rate has been increased because we have this decrease in the activation energy here. So that's the foundation of how enzymes work in biological systems, and then we're going to look a little bit deeper into what exactly is the transition state theory and how that works in there in the next